Hi, and welcome back. Unit 6.2. This is part 2 of 2. So in part 1, we talked about how we measure the concentration of a solution using a spectrophotometer. And we talked about how that sort of works where you're measuring the amount of light absorbed by a sample, amount of light at a particular wavelength absorbed by a sample. And that tells you the absorbance. So this is useful in conducting a rate experiment where you want to measure the concentration of either the reactant or product. In this case, it's the reactant over time. And we have a blue reactant A, and over time, as the reactant gets used up, the solution becomes less and less blue because we're using up that substance. So this would be a plot of the absorbance at the wavelength that we measured the concentration of A at, or the absorbance of A at. And you will see over time it starts to decrease. Now, because absorbance is directly related to the concentration through this equation here, we can also use the absorbance that we get in this from the spectrophotometer. We can use that absorbance to determine the concentration. And of course, then we can plot the concentration over time. So either organize it in a graph or plot it. And in both cases, we can analyze this for the average rate or the instantaneous rate. So although we can use this data to get our average rate or instantaneous rate, the question then becomes, well, how do we use it to determine a rate law? After all, that was sort of how we started this 6.2, is finding another method for determining rate law. So you may be wondering, well, why isn't the average and instantaneous rate enough? Why do we even need the rate law? So let's be clear about why the rate law is important. The rate law is important because, as you know, the one factor that controls rate is concentration. And that's not always true, but for most reactions, the concentration of substance will control the rate. So since the rate is determined by concentration, the rate law expresses that. What we can do is, if we know the rate constant for a given reaction and we know the rate order for that reactant, we can use that to predict the rate for different concentrations. So we don't have to keep doing a bunch of experiments to predict the rate of a reaction once we have the rate law. So now the question is, well, how would we use data like this plot, to find the rate law? Because remember, to find the rate law, we need the rate constant, our K, and then the rate order with respect to that reactant. So it turns out, actually, that you can get that from the plots of concentrations versus time. And you can get two pieces of information. You can get the rate orders from these plots, and you can also get the rate constants. So let's look at these in turn. There are basically three types of rates that we're going to be looking at: zero, first, and second order. Let's start with zero order, since that's the simplest. So if you have a reaction A going to B, and you plot the concentration of A versus time, and if you get a linear plot with a negative slope, then you know the rate order of the reaction is 0. So N, which is what we're using here as the variable for rate order, will be 0. All right, and after you substitute this number 0n, you're going to get that rate is equal to, because anything raised to 0 power is 1, so you'll get that rate is equal to k. The other thing to note is that k will be equal to the negative slope. So both of these pieces of information will allow you to find both the rate constant, which is the negative slope, and to solve for the rate of the equation of the reaction. Let's look at a case where we have first order. So let's say the reaction is first order, and you plot the concentration versus time, and you get this sort of like curve plot, somewhat exponential-like, right? And so if you notice that you have a curve plot, the first thing you want to try is taking the natural log of the concentration of A. So taking the natural log of the concentration of A versus time, and then plot that and then see what it gives you. And if it gives you a straight line with a negative slope, then you know the reaction is first order. So that means that N, the rate order, is 1. And the value for K, or the rate constant, is going to equal to the negative slope. So For first order, the key piece of information is if you get a linear plot from natural log of A versus time, then you know it's first order. Okay, let's take a look at second order. So let's say for second order, if you plot, starting again, you start off with concentration versus time, and you once again you get a curved plot, and you're like, oh, okay, that's curved. Well, let me go ahead and try that natural log of A versus time. So you take the natural logs of all your concentrations of A and you plot that, and you still get a curved line. Uh-oh. Well, then you have one more thing that you can try, which is taking the concentration of A and dividing it by the concentration of A and plotting that versus time. So if you do 1 over the concentration of A versus time and you get a straight line, this time with a positive slope, then you know it's second order. That means that or our rate order here would be second order. So you can go ahead and plug that in, and this will be your rate law. Rate is equal to K times A to the second power. And in this case, the slope of the straight line that you get here is equal to K. So you can also find the rate constant from that slope. Okay, so here, let's try a CFU2. The rate for the reaction A to B is rate is equal to K times concentration of A to the second power. So that means it's second order. Which of the following graphs would you expect to give you a linear plot? Natural log versus time, 1 over concentration versus time, natural log versus time, and this time with in the first case, you had a curved slope. This one you have a negative slope here, and then A versus time. So which one of these graphs would match this rate law? Okay, so the answer is the second one because it's second order. For second orders, it's 1 over concentration of A versus time. That would give you the straight line. Okay, here's our next CFU3. You're going to use the plot of concentration of A versus time to write the rate law for this reaction. So, and describe how you use the graph to write the rate law. So why don't you give it a go? See if you, what methods would you use to sort of figure out the rate law? And then, but if you need a hint, pause, press play after you give it a go, and then I will give you a hint. All right, here's the first hint. You know that the rate law is equal to K times concentration of A raised to, in this case, I'm using X for the rate order. So that means if you wanted to find the rate law, you would need to find X. How would you do that? So you might want to think about which plot this is, and if the plot's linear. If it's not, you can test other plots, natural log of A versus time, 1 over concentration of A versus time. So pause the video now and give that a go, and then if you still need help, press play again and there'll be another hint. Okay, so here's the second hint. You have points on this graph. You can sort of estimate those points and then use that to develop a table. Remember, on the x-axis is the time, on the y-axis would be the concentration. This time it's in micromolar, but it doesn't really matter in terms if it's micro or just molar. And you want to try taking the natural log or 1 over these concentrations and see, and then plot that data to see which one gives you a linear graph. So you can try that and then pause the video again and I'll show you my work. Okay, so what I did was I took my values, I estimated the points there and I laid them out in a table. And then I got these values here. And then I took the natural log of the concentration of A. So basically this value is natural log of 50, this value is natural log of 17, natural log of 7, etc. And I plotted that. I also tried it with 1 over concentration of A just to show you. So I took 1 over 50 and I got this value. 1 over 17 got this value, and so on. And so there are my 2 plots. And as you can clearly see, the one which is natural log versus time is linear with a negative slope. And so that tells me that I have a first order. And so the method that I did was I just figured out which plot will give me a linear curve, and it turns out it's natural log versus A, and so that's how I knew the rate order was 1. Now, the other thing I can do, which I didn't do here, is I could actually use the slope of this line to find K. So just real quick, if we wanted to estimate the slope of the line, the rise would be 3 and the run would be 30. So it's about 0.1. So I can actually solve for my value for K from the slope. And remember, it's going to be negative value of slope. So let me just go ahead and do that. K is equal to negative slope. So that's equal to positive 0.1, because the slope was negative 0.1, so I get a positive 0.1 value for, and that's of course little k. Okay, so let's go into sort of like wrapping it up what we've done here. So to determine the rate law, remember the plot that gives you a linear graph tells you the rate order and rate constant. So if you have concentration versus A versus concentration of A versus time, and gives you a straight line with a negative slope, you know that the reaction is 0 order with respect to A, and the slope will be equal to K will equal negative value of the slope. If the natural log versus concentration, natural log of concentration of A versus time gives you a straight line with a negative slope, then once again that's first order this time, and you can use the slope to find K. K is equal to the negative slope. And then finally, if it's 1 over concentration of A versus time gives you a linear graph with a positive slope, then you know it's second order with respect to A, and the slope is K is equal to the slope. So one thing to note is that you can only find the rate of the order of the reaction of one reactant at a time. And so you may be wondering, like, if you had something like A plus B goes to C, how would you do that? How would you determine the rate order of A and B? And what we use is called a flooding reaction. It's sort of like a pseudo first order rate. And what we mean by flooding is you'll take one reactant. In this case, let's say we want to find the rate order with respect to A. So we'll have that at a low concentration, but we'll have B at a much higher concentration. And that's sort of called flooding. And so basically what it allows you to do, it allows you to ignore the effect the change in the concentration of B would have on the system or the rate of the reaction. So we can just focus on A. So let's say we did that and we've got natural log versus time gives us a straight line, then we would say that the rate order with respect to A is pseudo first order. We would try the same thing again, this time to find the rate order of B. So we would have a very, very high concentration of A. So we could ignore the effects of A on the rate, and a much lower concentration of B, and do our studies on B. And then once again, we could use our curve to figure out the rate order. In this case, 1 over B gives us a linear plot with a positive slope, so then that gives us our B. All right, so that's it. This is a good time to sort of reflect and summarize what you've learned. Hope you found this video helpful. Have a quality day.